Okay, and now Marcos will tell us how to verify graph algorithms using an algebraic approach.
Okay, so thank you very much for the introduction. This talk is going to be about separation logic and its problems with graphs. So separation logic is a method for verifying heap manipulated programs. Its main characteristic is reasoning about heap decomposition. This is achieved via its main connective, the separating conjunction, which formally states that P separating conjunction Q holds of a heap H if it can be decomposed into two disjoint heaps H1 and H2 such that P holds for one and Q holds for the other. The main specification pattern of separation logic involves describing the heap layout by predicates. So for example, we could define a list predicates such that we could specify that the heap H store a linked list between pointers I and j, for example. We will refer to this kind of predicates that describe the heap and other heap-related concepts as spatial. So these spatial predicates are often parameterized with non-spatial data. By non-spatial, we mean abstract mathematical structures. So for example, we could extend our list predicate with as non-spatial argument a mathematical sequence. This way, what we will achieve is, in the verification process, abstract away from the heap and reason instead about the mathematical sequence and its properties. In practice, this list predicate is defined inductively on alpha using star and other separation logic primitives, which will enable us to decompose this structure in the heap. So the purpose of this spatial decomposition is local reasoning, which is achieved with the help of the inference rule of frame, which involves disregarding the part of the heap that the program doesn't touch. This way, localizing reasoning to the heap that we really want to reason about. So if we're given a program that mutates the head of a list so that its contents change to point to B, we can actually decompose the list, disregard the part that we don't care about, apply the mutation, and then reattach the pieces afterwards. So an important observation that is not often made explicit is the fact that spatial decomposition induces non-spatial decomposition. What we mean by this is that in order to decompose the list in the heap, we first need to decompose the mathematical sequence via sequence concatenation. So this is trivial in the case of lists because of concatenation. However, for graphs, this is not the case because there's not such a notion of decomposition. So a popular potential fix was proposed in an early work of separation logic in 2001 by Young, where in a seminal proof of short-weight graph marking algorithm, he avoids graphs altogether. And he does this by, instead of relating the heap to the mathematical graph gamma, he relates it to multiple graph abstractions that approximate the structure and that are parameterized by structures that do actually decompose, such as sequences and trees. The problem with this is that these multiple graph abstractions are very tedious to synchronize with each other and with the heap, which amounts for most of the complexity of Young's proof. Furthermore, and most importantly for us, because you don't have the graph at the non-spatial level, you cannot neither construct nor use graph libraries. So our contributions begin by observing that graphs do generalize to support decomposition if we define them as partial commutative monoids. However, this is not enough. There will be cases where we'll need more algebra to localize the proofs. For that, we will introduce PCM morphisms, which will play an analog role to framing, but at the non-spatial level. This will enable us to localize reasoning even about what they are usually referred to as global properties. This will shift most of the reasoning from the spatial heap level to the mathematical non-spatial level, where graph libraries can be constructed and reused. This will lead to new and concise proofs of both benchmarks of short weight and union find. So let's now move on to see how we define graphs as partial commutative monoids. So to the question how to decompose a graph, we attempt a pictorial argument. So we have here the following graph with the following divide. So we argue that the way to decompose it is as follows. But however, this has the problem that one of the components is not strictly a graph, because there are dangling edges which are not usually considered in the classical definition of graphs. So from this observation, we conclude that we actually need graphs with dangling edges in order to make them decompose. And these are precisely what partial graphs are. We define formally partial graphs as finite maps from nodes to a pair, with the first element being the contents or marking of the node, and the second element being its adjacency list. Notice that because we allow for dangling edges, some of the nodes in the adjacency list may not be themselves in the graph. So this is a single node graph that which can be represented as A maps to the contents X and the adjacency list ABC. So partial graphs decompose with the join operation, which is defined as plain union if the nodes are disjoint and undefined otherwise. This operation is partial, commutative, and associative. And with the empty graph as unit, it conforms a partial commutative monoid. With this notion of composition, partial graphs compose and decompose trivially. The second notion that we introduce is that of PCM morphism. We will define it as a function f from A to B that preserves PCM structure. So we will emphasize here the second equation, which corresponds to the distributivity of the function f over the graph. This will be important. Some examples of graph morphisms are the nodes of the graph, the sinks or the nodes with incoming edges, any kind of filtering about the contents of the nodes, or any kind of mapping a function throughout the graph. All of these and many more are examples of graph morphisms. Each will have its corresponding distributivity equation. So as for non-morphisms, these will correspond to properties that are often referred to as global. This is the case because these are exactly the properties that, when decomposed, are not preserved. Also, it is possible the case that they are not computable from its individual parts. So an example of a non-morphism is the property of a graph being closed, meaning that it has no dangling edges. As we saw in the example of the decomposition of the graph, we began with a graph which was closed. When decomposing it, one of the subcomponents violated the property of being closed. Okay, so how do morphisms localize proofs? We begin by showing some analogies with the frame rule. So the same way the frame rule decomposes the heap by using the separating conjunction, morphism will decompose the graph, but in terms of the join operator. The same way framing localizes to the heap that holds of P, morphism will localize the subgraph gamma 1. And the same way framing removes from the specification the heap that holds of R, morphism will factor out gamma 2. As for the differences, there's one advantage of morphisms over the frame rule, which is that it is possible to rewrite inside any arbitrary context, while the traditional frame rule applies mainly at the top level of a specification. The second and biggest difference is the level at which each of these patterns of localization actually operate. So we have the frame rule, which applies at the spatial level of heaps and programs, whereas morphisms apply at the non-spatial mathematical level. The conclusion from this comparison is that we actually need both. So let's now see a concrete example of using morphisms in verification. So we need to prove the following lemma about the preservation of closure. So we suppose we have a graph gamma such that x is in between the nodes with two outgoing edges to, let's say, xl and xr. We note that the graph is closed and that y is also in between the nodes. Now let gamma prime be the result of redirecting the left edge of x in gamma to point to y. The lemma says that this resulting graph is closed as well. So I want to point out two things. First of all, that because of the PCM morphism, we have that the rest of gamma, which is not x, is actually unaltered. And second, that what we are asked to prove is actually a global invariant because, as we saw before, it's not a morphism and it does not distribute. So how do we proceed? So the key idea is that even though the property is not a morphism and it does not distribute, we can very often define it in terms of morphisms, and in that case, we will find the distributivity and the locality deeper inside the property. So we do just that, and we define it in terms of sinks and nodes, which we saw were examples of morphisms. So by saying sinks of gamma prime are contained in the nodes of gamma prime, we are saying that there are no dangling edges. So we proceed by equational reasoning, and we start from sinks of gamma prime, and we want to get that this is contained in the nodes of gamma prime. So we begin by rewriting by the definition of gamma prime. We then want to distribute so that we factor out the rest of gamma, which is not x. We are going to exaggerate this distributivity to make clear our point. And from now on, we will be reasoning about the single node graph x pointing to y and xr. So we begin by rewriting by the definition of sinks, which gives us y xr. Then by simple set inclusion, we get that this is contained in y union xl xr. And at this point, we again rewrite by sinks. And at this point, we can already rejoin the factored out graph by the distributivity equation, but the other way. This way, we get the sinks of gamma, which by assumption we know are contained in the node of gamma, and we also know that y is in nodes of gamma, so all is contained in the nodes of gamma. Finally, the last step is to prove that the nodes of gamma are contained in the nodes of gamma prime, which follows more or less the same pattern, so we will not get into the details. So as you see, we have been able to factor out the part of the graph that has not been altered and reason locally about this single node graph. So in verification in general, what we want to do is define the key properties of the algorithm in terms of morphism so that this pattern can actually apply. And this is what we do precisely for the case of short-weight graph marking algorithm. This algorithm marks reachable nodes from a given route. And the interesting part is that it encodes the stack for backtracking not as a separate structure, but by encoding the stack by reversing the edges of the graph itself during the traversal. So it achieves this with two auxiliary variables p and t, and 4 different node markings. So unmarked, left marked, right marked, and fully marked. The left and right nodes will encode the nodes that are part of the recursion stack. We will highlight those in red, and so let's see a partial execution. So we begin from the root, and we proceed depth first search. Notice how in the process we are swinging the edges so that the backtracking information is always maintained, all while marking the nodes. So in the end, an intricate thing to prove as a postcondition is that all the edges are restored back to their initial position. For this, we need a loop invariant that relates current graph, initial graph, and the stack. Remember, we want to encode this as a morphism in order to reason locally about it. So the first observation that we make is that the key transformation of short weight, that of reversing the edges, is node local. So it's expressible as a node local higher order function that branches on the marking. Once we have this function, in order to state that all the edges are restored, we apply it to traverse the stack. We iterate it over the whole graph by mapping it through gamma, and we finally equate it to the initial graph to relate to the starting edges. And because we know that mapping a function is a morphism, we have encoded this complex invariant in terms of morphisms, which will allow us to apply this pattern of localization. So this is the full invariant of short weight. Of course, we are not going to get into the details of it. However, I want to point out that all of these circled concepts are actually morphisms. And a similar situation happens in union find. So as conclusions, we have generalized the notion of graphs so that they support decomposition. And we have introduced morphisms as the non-spatial analog of framing. This way unlocking a new pattern of localization that enables local reasoning also about global properties such as closed and the loop invariant. And this has shifted the amount of reasoning from the spatial level to the non-spatial level where libraries can be built and reused, which result in very concise mechanized proofs. So more precisely, the proof of short weight takes 110 lines of rock and union find 49. Of course, all of this being supported by a general graph library of reusable lemmas. So this is the artifact, and that's it. So thank you very much.
So like which separation logic did you use in ROC? And is it like agnostic to it or?
Yeah, so it's a standard separation logic from early papers on, yeah.
Which one?
Yeah, from 2001, Peter and Hearn and company, yeah.
But like, do you think it would work on
so
Iris?
It's not, so in ROC, we don't use Iris, we use Hoare type theory, which is a type theory that is used to reason about separation logic, yeah. But this method is general in the sense that if you have framing and separating conjunction, you can actually apply it and get the same results. So yeah.
Hey, thanks for the talk. So, I mean, I think it was a lot of fun. So the one thing that wasn't really clear to me is it's like, so like we say that sort of for this technique to work, we need to rephrase things about graphs in terms of these partial commutative monoids, right? Mm-hmm. But then it's like, once we rephrase them, how do we reuse a general graph library? Because a general graph library will be talking about stuff in terms of vertices and edges or whatever, right? So like, it's not clear to me. Like, do you need to write a specialized library for PCMs and how they relate to graphs, or like what? Like
right. No. So it's a general graph library where graphs are defined as PCMs.
Ah, okay.
So it's general in the sense that this definition and the spatial predicate of graphs can be applied to multiple algorithms.
Right.
So
okay.
We've used it for short weight and union find, but any algorithm. Any graph algorithm can actually use the same predicate with the same definition of graphs.
Right, okay. So then I guess that brings me to my second question, which is, so like, if we think about, or like, I mean, in the example that you showed where you defined this closed predicate, right?
Yeah.
It was like, like you needed some amount of cleverness in order to redefine it in something that does actually like distribute correctly, right? Like in terms of the, right. Yeah. So I mean, I guess my question is like, I don't know, is there like a textbook already that tells me when I redefine things in terms of PCMs, how to take all the concepts that I'd find in like undergrad graph theory in a way that works well and distributes nicely? Or is it that like you had to come up with the right definitions for your particular thing, and there's still open research to be done on coming up with definitions that work well with
Yes, there's definitely not a textbook of how to define things in terms of morphisms. So that's, I think, the main thing that you have to reason about when verifying following this approach. That so you have these properties that changes throughout depending on your algorithm, and you have to figure out how to actually define it in terms of morphisms. Yeah.
Okay, thank you. I'd be interested to chat a bit more later about this library design. Yeah.
Yeah.
Thank you. Hi.
Yeah.
So
hi.
I'm confused about this distinction you have between the sort of pure logic and then the separation logic. So, but do I understand correctly that the pure logic also?
No. Well, so at the spatial level that we call it, it's the heap. So you have pointers and maps to and the separating conjunctions, and then what the non-spatial level is where mathematical structures live. So you can the sequence in the case of list and the graphs in our case. So.
And that is also a separation logic.
Well, it's part of it. Yes, it's like a different level of reasoning about it. Yeah.
Okay, so it's like you have two separation logics with different with different logical resources.
No, so so it's one separation logic, but you parameterize these predicates that specifies the heap in terms of mathematical structures, and these mathematical structures can be anything that you can define in pure mathematics.
So you have two instances of a single separation logic. No.
Not exactly. No.
I think I should read the paper maybe.
Maybe yeah, and I can explain further if yeah.
Okay. Yeah. Thank you.
Yeah.
Hi. Thank you for the great talk. So I'm wondering if you consider a tree and an invariant on a tree that also like talks about the heap resources, and if your tree invariant needs to, like for each node, if it needs to keep some information about all of its children, will your technique help to make reasoning like localize for each node?
Well, for trees, there is not so much problem as with graphs because, there has been work on trees that uses like traditional methods, and there hasn't been, or at least they haven't been explained that there were any problems with it. So, but of course, the same things about trying to specify your properties in terms of morphisms will as well apply. So I don't know in this which morphisms would apply in your specific case, but very often it is the case that you can actually do that. Yeah.
Right. Thank you.
Thank you. So let's thank the speaker again.